This is the first part in a three-part series for how to use the chain rule. At the end of this video, I'm hoping you can break apart compositions of functions and use the chain rule to find derivatives of those compositions of functions. At the beginning, we're going to go in one direction. We're not going to do everything. And, well, we're just going to do basic building blocks here in the first video. I think this is going to be a three-part video series. So what's a composition of functions? Well, we have y is sine of u, but I'm just going to say sine of something because that u is another function. So we think of this as, hey, we have y is sine of something, and that something is x squared. You would normally see just, hey, sine of x squared, all in one color, but I want you to see how these pieces are put together. If we're going to take the derivative of a composition of functions, well, we need to have them broken apart. We'll work on breaking apart compositions in a moment. But you can do the derivative of sine pretty easily. The derivative of sine is cosine of, well, of the same thing. And the derivative of x squared is 2x. But we want to make sure we have the right notation. Now, we could write y prime and u prime, but those don't have a bunch of information that might be useful later. So instead of y prime for the derivative of sine of u, we're going to say d something over d something. And turns out that's going to be dy over du. Y is the output variable, u is the input variable. We're going to have a similar notation for the derivative of u with respect to x. We're going to write du dx. Well, we're normally writing dy dx. I guess we think of x as the normal input or the most common input and y as the most common output. And we have all the correct building blocks. We have dy over du and du over dx. And those du's can divide. There's a name for each of those little pieces. Those are called differentials. I don't think we're there quite yet. But anyways, you can see dy over du multiplied by du over dx is the same thing as dy algebraically. We're not going to worry about y today. Y the question, not y the verb. So I'll bring down dy over dx. That's kind of the same thing over here on the left. And we'll replace dy du with cosine of u. Replace du with, or du dx with 2x. But that doesn't look quite right, because if I have, what, dy dx, I expect to have a whole bunch of x's. So can we get rid of that u inside of the cosine? Sure. We can put what u is equal to, namely x squared, in there, and we have, okay, dy dx is cosine of x squared times 2x. So what does that really mean? Well, if we had composed, which we did earlier, well, the derivative of sine of x squared, that's really what we would start with. The derivative of sine of x squared is cosine, still of x squared, and then multiplied by an additional 2x. All right, let's see that again. So how would we compose some function squared if that function is sine? Well, I see that squaring function is a little empty spot with things squared. What are we squaring? We're squaring sine of x. You wouldn't normally see everything written that way. You would see y is sine squared of x, which does mean the sine function is squared. So how would we do derivatives? Well, derivative of u squared is just 2u, and the derivative of sine of x is just sine of x, cosine of x. What notation are we going to use? Well, we took the derivative of y with respect to u, so dy over du, and we took the derivative of u with respect to x, so du over dx. We're really looking for dy over dx. Maybe we can think of that as a tiny change in y over tiny change in x. An instantaneous rate of change, maybe slope of a tangent line, dy over dx. How do we get that? Dy over du multiplied by du over dx. And so what do? We replace dy over du with 2u and du over dx with cosine of x. And we get dy over dx is 2u times cosine of x. That doesn't look quite right. Let's get rid of that u, replacing u with the sine of x we started with. So dy dx, or some derivative, is 2 sine x cosine x. What's that the derivative of? Well, we might as well recompose. If we put this top part together, we get y is equal to sine squared x. So sine squared x has the derivative 2 sine x cosine x. If you were sitting in my classroom, we would go through this quickly. In the next video, we are going to do this a second time as we are doing this chain rule stuff. We're doing the derivatives. So, can you see the composition here? I like to say inner and outer function, and I guess what I'm saying with outer function is the last thing you would do in terms of order of operation. So if I give you an angle x like pi halves, what would you do first? Turns out you would do cosine first. So the outermost function here is the cubing function. Turns out cosine is the thing that's being cubed. So how do we break that apart? Well, the thing inside, we're going to call that u. So u is cosine of x. And then what's the blue part? Well, we would just write y is u cubed, or just y is something cubed. And then what's the thing that's being cubed? Cosine of x. This should be a little bit easier to see what function is the input to another function. And, well, cosine is the outer function, and sine is the input to that outer function, cosine. So we're going to say u, that innermost function, is sine of x, and y is, well, cosine of that inner function. Y is cosine of something, that something is sine of x. This is probably getting a little bit easier. What's the inner function? What's the outer function here? Well, cosine of 4x squared. By the way, that word of, if you're reading things out loud correctly, that word of is an indication of an input. So this is cosine of 4x squared. 4x squared is the input to the cosine function. So we're going to say the input, or u, this new placeholder. School's out. This placeholder function, u, is 4x squared, and we'll say y is cosine of u. So here you should be able to see the inner function and the outer function. And that is, what do we have here? This is a cubing function with an input of 2x minus 7. So u is 2x minus 7, and we are cubing that 2x minus 7. All right, I believe one last decomposition here, and then I'll pause the video, and we'll make a new one. So what's the innermost function here? Well, if you read that, 3 sine of 2x cubed. I guess you could say there's a multiplication by 3, but really we're talking about input. So 2x cubed is the input to sine. So we're going to say u is 2x cubed. And I guess we're going to rewrite y as 3 sine of u, or 3 sine of something if that something is 2x cubed.